I repeated this slide because it is the gist of what we want you to know. A unit cell is a cube, and we are looking only at cubic unit cells. We really want to make sure that you know if an atom is at a corner, that 1/8 of it goes into the unit cell, that if it's on the face, we want you to know that 1/2 is within the unit cell, and when they say anywhere else, that's usually in the center, and that would count for 1 full atom. Yes, some might be on the edge. That's kind of the other way that can happen, but familiarize yourself with this so that you're very confident that you can use those numbers. Again, repeating the edge length because essentially you can go from an edge length to a density, but you can also go from a density to an edge length. And please do, there's only one homework problem that has you do that in the entire book, and that is 12.60. Again, a lightweight chapter. A lot is in here, but we really aren't going to emphasize it for your class. Here again is the crystal structure of sodium chloride. I emphasize again, please do 12.57 and 12.58. Don't skip it because there may be a question and they're very easy once you figure out how they work. So the last thing to cover is the close packing of spheres. We are going to assume that they are uniform size for chemistry 1210. We're going to say that all the attractive forces are maximized. If it's a positive and negative, you know that. And we're also going to use something called close packing. I often tell students, think of when you're playing pool and you rack the balls up and how they touch one to each other. That's essentially what we mean by close packing. In our class, we want you to know about 2 different kinds. One of them has the title hexagonal, HCP, and it's an A-B-A repeating pattern. Take some time and think about it. I normally hold these things up in class. I can't do that here. The other one is called a cubic close pack, and essentially what it is an A-B-C. So see how this is called cubic close pack? See how there's just a different ordering. On the next slide, I show it as you go layer by layer. So here would be our top layer. That would be our layer A. Here would be our layer B. And then we could either have another A or we could go A, B, C. Again, we cannot go into great detail. This is fascinating information, but we just can't do it. The other thing to note is that, see this large gray that is big? See this little red that is very, very small? Well, what's usually very small? A cation. What's usually very big? An anion. So when you have an ionic material, the cations, which are small, normally sit in the holes in between the cubic close pack. Finally, coordination numbers. Students have had a very hard time visualizing this, so I'll try my best here. When we have a simple cubic, the first one, notice the red atom in the center. Notice the coordination number is 8. I've never really been able to explain these two, so I'll just say it this way. If I have a material like NaCl, its coordination number is going to be 6. If I have a material like zinc sulfide, its coordination number would be 4. Know that there's many, many, many different ionic materials. Each one has to be carefully analyzed because the technique, again, is X-ray diffraction. And when we talk about a crystal structure, we normally say that it is organized. And in this class, we talk about a unit cell, and we say that it is cubic. Again, the chapter has a lot more. It's got really interesting questions, but we do not need to go there.